Alright, today we'll be looking at network flow. Um, I'm not really an expert on the subject, but I'll try my best to explain everything. So, let's first go over what a flow network is. So, it is a tuple of a set of vertices, a set of edges, a source node called S, a sink node which is called T, and then a capacity. The capacities on each edge are non-negative, and you can think of this as just uh, maybe the edges are pipes, and a certain amount of water can flow through it at a time. So that's the capacity. It starts at some source, and then it is sent through the network until it reaches the sink. Now, an ST cut is a partition AB of the vertices with S in A and T in B. So we're splitting it into two sets. And the capacity of the cut is the sum of the capacities of the edges from A to B. So you can imagine we're separating the network by cutting out these edges. And then we have one set here and another set here. So here the edges have capacity 10, 5, and 15, so the capacity of this cut is 30. So here we've changed it. We selected these three nodes as our set. And then this is the other set. And we've cut along these edges. And here we do not include edges from B to A, just from A to B. So we want to find a cut of minimum capacity. For example, here, this is less than the 30 we had earlier. Here we cut along this edge, and this edge. Okay, so an ST flow function is a function which satisfies that the value of it for each edge is between 0 and the capacity. And for every vertex which isn't the source or the sink, the flow going the flow going into the vertex is equal to the flow going out of the vertex. So if we look at this node, for example, we have 10 flow going into it. And we have 5 going out here and 5 going out here, which is 10 in total. For this node, we have 5 going into it and 5 going out. Because this edge has 0, this is 5. So we have flow conservation. Now, the value of a flow, f, is equal to this sum. So how much flow goes out of S minus how much flow goes into S. So right now, there's nothing flowing into S. So it's just the sum of the outgoing edges. So that's 10 plus 5 plus 10 equal to 25. And because of the flow conservation, we then know that 25 goes through the network and reaches the sink. And here we have the max flow problem, which is finding a flow of maximum value. Now we're going to look at the Ford-Fulkerson algorithm. Okay. So we're going to try a greedy approach. We'll start with flow of all edges being equal to 0. And we'll find a path from S to T, often called an ST path, where each edge has the flow value less than the capacity. So for each edge we look at, the current flow value here, like here, has to be less than the capacity. And then what we do is we augment the flow along path P. And just repeat this until you get stuck. So here you find the path. And we see on each edge we have flow 0, so everything is less than the capacity. So we augment the path, and we can augment it by 8 max, because this edge here has 8 capacity, but the others have 10. So we use the minimum here. Then we find another path. This is still less than the capacity. It's less than the capacity, and these two as well. But here we have capacity 9 and capacity 2. But also we only have 2 left to fill up this one and this one. So our bottleneck's gonna be 2, and we augment the value by 2. So currently our flow is 10. Right here the bottleneck is gonna be 6. So we augment the value by 6. And we got 16. But the max flow value here is 19. We could have done better. So why did this happen? Once we increase the value of an edge, we never decrease it. And the max flow is unique in this example here. And what could happen is that the algorithm chooses to go first for S, V, W, T. And the optimal thing to do in this case is to pass the flow along these edges and then these edges, so we get 4. But if we do it in another way, like this, if the greedy algorithm chooses this path first, then we get 1 from here. Then we can add 1 here and 1 here, so we get 3. So what we need here is we need a mechanism which can allow the greedy algorithm to undo a bad decision. So our original edge is from U to V, and it has flow and capacity. We create a reverse edge, which allows us to undo flow that has already been sent. So, for example, here we have flow 6 and capacity 17. This would change into an edge with value 11 and an edge with value 6. So this is how much flow we can send, how much more remaining flow we can send. Yeah, it's called the residual capacity. And then as we set this 6 flow along this edge, we have to make sure the reverse edge gets 6 added to it, and this gets 6 subtracted from it. Okay, so an augmenting path is a simple ST path in this residual network. And the bottleneck capacity of an augmenting path is the minimum residual capacity of any edge in the path. So if you let F be a flow and you let P be the augmenting path in the residual network, then after calling augment, the resulting F prime is a flow, and the value is going to be the previous value plus the bottleneck. Maybe allow you to read the code. So here we get the bottleneck, and then for each edge in the path, we increase the flow going through the value by B. If it is the reverse, we subtract. Okay, so the Ford-Fulkerson algorithm, we start with the flow as 0. We find an ST path in the residual network, and then we augment the flow, and you repeat this until you get stuck. So now we have this mechanism of undoing. So first we initialize here, then we get the residual network, and then just repeat while there is some path, augment it and get the flow, and then update the graph according to the flow. Update the capacity, the residual capacity of the edges. Okay, so let's look at the relationship between flows and cuts. So if you let F be any flow and you let AB be any cut, then the value of the flow will equal the net flow across the cut. So here we have the set A, and the value is going to be this here, the edges going out of A, and then as before you could have something going into the source, so you just subtract that, but in this case we don't have any. So then we get 5, 10, and 10. Here you also get 10, 5, 10. And here we select this set. Okay, so here we have an edge going into A, into A, into A, and into A. So if we add up these edges going out of A, and we subtract the edges going into A, we get 25. The same as the flow. So the proof of this just depends on the flow conservation. All the terms here are gonna be 0 except for when v is equal to s. So we'll just get what goes out from s, which is gonna be the value for flow. So if you let f be any flow and AB be any cut, then the value of f is gonna be less than or equal to the capacity of A and B. So here we have the value, which is this expression here. Now, if we just remove this term we're subtracting here, then we get this. So this here is going to be less than or equal to this here, since we could only possibly increase the value. This is non-negative. Now, this sum here is less than or equal to the sum of the capacities, because each term, or each f of E is less than or equal to C of E. And this is just equal to the capacity of A and B. Okay, so if you let F be a flow and let AB be any cut, if the value of the flow is equal to the capacity of A and B, then F is a max flow, and AB is a min cut. So for any other flow, the value of that flow is going to be less than or equal to capacity of A and B, which is equal to the value of F. So this can't increase. This is the maximum we can obtain. And similarly for any cut, it's just the other way around. We can't get a cut with a lower capacity. So if there are no augmenting paths to find, then the flow f is a max flow. And so the max flow main cut theorems just states that the value of a max flow is equal to the capacity of a main cut. And the following three conditions here are equivalent for any flow f. First one being that there exists a cut AB such that the capacity of A and B is equal to the value of f. And f is a max flow. And then also that there is no augmenting path with respect to f. Okay, so if you suppose that AB is a cut such that the capacity of the cut is equal to the value of the flow, then for any flow f prime, its value is going to be less than or equal to the capacity of AB, which is equal to the value of f, so f is a max flow. This proves statement 1 to statement 2. Statement 1 implies statement 2. For the next one, we'll be flipping it around. We're doing the contrapositive, so we're gonna prove that not 3 implies not 2, and therefore 2 implies 3. So suppose there's an augmenting path with respect to f. We can improve flow f by sending flow along this path, thus f is not a max flow. And from 3 to 1, so if you let f be a flow with no augmenting paths, and you let A be the set of nodes which is reachable from S in the residual network, so if we have here a back edge, yeah, we could have back edges here as well, and then we cannot reach some of the nodes. So by the definition of a cut, S must be in A, and by the definition of flow, T is not in A. So we have the value of the flow, and following these steps, sorry, my sound cut out. Yeah, following these steps, we get the capacity is equal to the value of f. Okay, so I want to code this algorithm up with you. But we'll need a problem to test it on. So let's see. Okay. So here we have a problem where we have nodes, which are machines, computers, and they are connected by some paths, and these paths have bandwidth. So we have some connection between two nodes, and the connection between these two nodes has some capacity, which is a bandwidth. And we are given a starting node and an ending node, and we want to know what is the bandwidth between them. So this is just a classic example of max flow. Okay. So let's start with our main function, and we'll assume we have a class which handles this for us. Sorry. Okay. So we need an integer n and the nodes are numbered from 1 to n. The next line contains 3 numbers s, t, and c. And then there are c connections. Alright. And then we have to print the number of the network. Okay, so we'll start with network 1. We'll read into n, and they said that a line containing the number 0 follows the last network description. So n is not equal to 0. Okay, so we'll assume we have a class called flow network, and we'll instantiate it with a number of nodes n, and then we need s, t, and the number of edges. I'll call it m. And since they gave us the values 1 indexed, we have to subtract 1 from s and t. So you want to go from, for all the edges, read it in and add it to our class. So we need starting point, ending point, and capacity. And this is 1 based, so subtract 1. Now we want to add the edge to our graph, so we'll use g, and suppose we have a function called addEdge. Now in this problem, the edges here are bidirectional, so you can have 5 flow going this way or this way. So here we'll add a reverse edge as well with the same capacity. And then all we have to do is output the correct thing. So we'll say network.
We have forgot to return to S, T, and M.
That's true. Thank you. So we'll write out the value of at and then increase it. I'll do it differently. Like so. Then increase at. And then we want to output the bandwidth is and then the value. The bandwidth is, and here we call our class G. We get the max flow from S to T. And then we're supposed to have a period at the end, full stop. And print a blank line after each test case. Okay. So now let's write the Ford-Fulkerson algorithm. So here we define the flow network. And for the flow network, we'll need a structure for our edges. So let's start with that. We have U, V, and capacity. We'll have the reverse edge. We need to know for each edge which is its reverse counterpart. And then we need to know whether an edge is a forward or a backwards edge. And then the constructor for this will be, we need the value of U, we need the value of V, we need the capacity value, and whether it's forward or backwards. So U takes the value of U, V takes the value of V, capacity takes the value of capacity, and forward takes the value of forward, and then nothing else in the constructor. Okay, so that's our edge struct. Okay, for the graph itself, we need the number of nodes. So that's n. We'll need the adjacency list, so that'll be a vector of edges. We'll have it as edge pointers because we want to be able to have a pointer to the reverse edge for each one. So we have the adjacency list, and then we need our constructor. So a flow network which takes one value n, and then this needs to be like so. So n takes the value of n, and our adjacency list is initialized with the value of n, so it becomes a list of size n. Then we need to define our add edge function. So add edge, it accepted u, it accepted v, and capacity. So the forward edge defined is gonna be e, which is a new edge from u to v with capacity, and it's forward, so true. The reverse edge, rev, is equal to a new edge which goes from v to u with 0 originally, and it is a backwards edge, so false. Then we say that the reverse edge of e is equal to rev, and the reverse edge of rev is equal to e. And then add the edges to the adjacency list, so for u, push back e. For v, push back rev. Okay. So the max flow function we have a source and we have a sink. And we start with flow equals 0. Then we loop until we find a reason to break. And what we want here is we want to find an augmenting path. So we'll have another function for that. So let's say we get the flow from the augmenting path. So augment from the source to the sink. If we don't increase the flow by anything, so if f is equal to 0, then break from the loop. There's nothing left for us to do. Otherwise, just add it to the flow and repeat. Okay, and at the end we return it. Return the flow. Okay, so now we need to find augmenting paths. So, how do we find a path from S to T? Source and sink. We went over two versions of doing it. There's the depth first search and the breadth first search. I'm gonna use a breadth first search, and I need to retain the path, so I have to store for each node how did I reach there in the breadth first search. So we'll have a vector of edges. That will be our path. So we're gonna store which edge we use to reach each node. So we'll need n of these, one for each node. And yeah, so these are pointers, so we have to initialize them with null originally. So we can do it like so. just take the value of null, convert it to an edge pointer. C++ specific. Don't have to do stuff like this in Python. Then we need a queue for a breadth first search. So our queue, we start at the source. And we'll need a different value here to know we're at the end. So back of S. We'll just do this. Okay. Now while Q is empty, Q is not empty, sorry. We want the front value, so front value, and then pop it. Then go through all the edges in the adjacency list. Get the edge, or the node we're going to, so that would be UI, but this is an edge, so we need to get the V value from that edge, so like so. And then if we have not already set the back edge, for the node B, so if this is equal to null, we haven't set it already, and we can pass some flow along here, so that's gonna be here's cap greater than 0, so we have some residual capacity remaining. Then we want to mark this as visited and add the back edge, so we'll say back of V equals the edge we took, and we push it to the queue. Okay. So perhaps we could not reach T, and then there's no augmenting path. So back T equals null, return 0. Okay, otherwise we want to go through the path and find the bottleneck. What's the bottleneck of this path? And we want to subtract that bottleneck value from all the edges in the path and increase it on the reverse edges of the path. So we'll have a stack of edges, and we'll start by pushing the edge that took us to T. And then the bottleneck starts as the capacity of that edge. And then while the top of our stack, the starting node of the edge on the top of our stack is not the source, Oh. So while we haven't reached the source, we're gonna push the edge that took us to this node and take the minimum for the bottleneck. So push onto the stack the edge that got us to the value on the top of the stack, the starting vertex, like so. And then update bneck by taking the minimum of the current value of bneck and the newly added top value. Okay, so now we have the bottleneck. Now we just need to go through the edges again and modify the graph. So while the stack is not empty, so we'll have to take the current top value of the stack, modify its capacity by subtracting the bottleneck. And we have to look at the reverse edge for this one as well. So the top, reverse, and we add to the capacity there. And then we pop this off the stack so we can move on to the next value. Okay? And this bottleneck is going to be the value of this augmenting path. So we're going to return the bottleneck. And then we have our Ford-Fulkerson algorithm. So let's see if this gives us the desired result. Oops, one typo. Just be capital Q. Okay, so we have 4 nodes. We have yeah, 1, 4, 5. So that would be start, the source, the sink, and 5 edges. And then we have edge from 1 to 2 with value 20. 1 to 3 with 10. 2 to 3 with 5. 2 to 4 with 10. And 3 to 4 with 20. Network 1, the bandwidth is 25. Okay, so this gives us the correct result. And then end with 0. Any questions? All right. Okay, so let's analyze the algorithm. The capacities are integers between 1 and c. So c is the maximum capacity on an edge. And throughout the algorithm, the flows f of e and the residual capacities as well, these are all integers. So our algorithm is going to terminate in at most n times c iterations, because each augmentation is going to increase the value of the flow by at least 1. And since we do a BFS, needs iteration, then the running time is going to be O of m and c. So if c is just 1, the running time is O of m times n. And yeah, we have the integrality theorem. So there exists a max flow where every flow is an integer. So the flow of each edge is an integer. So is this Ford-Fulkerson algorithm as presented here? Is it polytime in input size? What that means is we can have m, n in some polynomial power, but the capacity we can only have logarithmic. We have to have it log of c. We can't have it in any power. So we have a similar graph as we had before when we were looking at the greedy algorithm without the undo operation. But here the edges have capacity c, which you can imagine is some really large number, such as 1 billion.
What do you mean by the? Why log c? That sort of escapes on me.
It's just the definition of polytime. You have so our input sizes are n and m, and then we have some values in our problem c, which are not exactly the input size itself. So we're allowed to have a polynomial in terms of m and n, but we cannot have c there as well. So as we did here, we have c to the power of 1. So that means this is not polytime.
I see. And log c is?
Yeah.
Why?
I don't know. This is. I've never really thought of it that way. I always thought of polytime as the input size, just n and m, are what matters, and then you have. I believe it's called quasi.
Yeah, pseudo polytime.
Pseudo polytime. So, yeah, I think this is just a matter of removing pseudo from there, because like the knapsack algorithm is pseudo polytime.
Which algorithm?
The dynamic programming algorithm which solves the knapsack problem, because then you have weights on items, and it takes time proportional to the weights of the items, not just the number of items.
Right.
Let's see. Let's see if we can. Just find the original definition. I'm not finding it.
I mean, it's not sounding like it's super important.
Yeah, I'm not finding a just some official definition, but yeah. I mean, whether you allow C to be a part of this at all, or just allow the logarithm of C, I mean, it's often not that important. But here we want to allow log of C to be polytime because that's what we're gonna give. But yeah, so if you consider what happens here is if we always take this path here, we always increase the flow by 1. So we're taking a large number of steps, which are kind of unnecessary because we could just augment the flow here by C and here by C. And then there's nothing left to do. So we have to be careful when selecting these augmenting paths because some choices are going to lead to exponential algorithms, and if we do something clever, then we can get something that's polynomial. So let's choose augmenting paths so that we can find them efficiently in few iterations. So we'll do something which is selecting the fattest path. So that means the max bottleneck capacity. There's also just choosing a sufficiently large bottleneck capacity possible, and then as well the fewest edges. So if we choose an augmenting path with the highest bottleneck capacity, it will increase the max flow by a large number of amount. So basically as much as we can in just the first iteration. So instead of just finding the absolute max, let's make it a bit simpler. We just want to find something that's pretty high. So we'll have a scaling parameter, delta, and we'll create, or we'll work with a network, G of delta, which is the residual network where you only have the edges which have capacity greater than or equal to delta. So here we have a network, and we set the delta to 100, and then this edge with 1 disappears. We only have the edges which are greater than or equal to the delta. So just start with the largest power of 2, which is less than or equal to the max capacity. And then we iterate. We get the residual network with the delta scaling parameter, and then we try to augment the path in that network. And we do the same as we did before. We get the flow of the augmenting path and we update the graph. And then if we finish and we don't find another augmenting path, we just reduce delta by a factor of 2. So we set delta equal to delta divided by 2. And we repeat this while delta is greater than or equal to 1. Okay, so how is this better? All our edge capacities are going to be between 1 and c, and all our flows and residual capacities are going to be integers. So if the capacity scaling algorithm terminates, then f is a max flow. We stop when delta goes past 1. So by the integrality invariant, when delta is equal to 1, the residual graph with the scaling parameter delta is equal to the original residual graph. And after that phase terminates, there are no augmenting paths. The outer loop we have is going to repeat 1 plus log of c times. This is because we decrease it by a factor of 2 in each iteration. And there are going to be at most 2m augmentations per scaling phase. So this gives us an algorithm which is faster. It's gonna take m log c augmentations, and it's gonna run in m squared log c time. Yep, so it may not be entirely obvious that this works, so that the scaling doesn't break things. So essentially, at each turn we're only considering edges with residual capacity greater than this delta. So nothing really changes except just the value we're allowing ourselves to take. We've reduced the minimum bottlenecks allowed. Otherwise, it works in the same way. So the flow, max flow, is still preserved here. And the proof before, we basically use the same method, except here we have this delta, we're subtracting, and then we're summing up deltas here. So then we have the sum of all the capacities of the edges going out of A. We subtract a delta for each edge going out of A, and then also subtract delta for each edge going into A. So that's all the edges here. And thus we get that this here has to be greater than or equal to the capacity of the ST cut of AB minus all the edges in the graph times delta. Another method of making the max flow algorithm better is shortest augmenting paths. So which augmenting path do we take? The one with the fewest edges. And this is done with BFS. That's what I did. So you find the path using a BFS and augment the path and then update it. Update the graph. So if we analyze this a bit, throughout this algorithm, the length of the shortest path is never gonna decrease. So the first shortest path that we find is the shortest path we'll find. So after at most m augmentations of the shortest path, the length of a shortest path will strictly increase. So the shortest augmenting path algorithm will run in O of m squared times n time. We'll have O of m plus n time to find shortest augmenting paths via BFS, O of m augmentations for paths of length k, and if there is an augmenting path, then it is simple. K is going to be less than n. It's going to be between 1 and n, not inclusive at the end. And we're going to have O of m times n augmentations in total. So you take this time complexity, you multiply it with this, and then you get O of m squared times n. So something you do with BFS is you sometimes look at the level graph. So a level graph is defined by the level it is at. So each node has the level it is at. It's just the number of edges in the shortest path from S to V. So it's just the distance really. And then we only the level graph is a subgraph of G which only contains the edges where the level increases between them. So like here we have level 0, 1, 2, and 3. And the reason we skip this edge in the level graph is because this is level 1 and this is level 1. So this is not increasing by 1 here. If there were an edge going from this node to T, then we would also skip that one because it's increasing by too much. It's going from 1 to 3. But of course that can't happen because then the shortest path here would be 2. So we only need to check if it's equal to L of V plus 1. And then we retain the edge. That's the graph we create. So you see how this separates the graph into these levels. So first we have level 0 here, then everything here is level 1, everything here is level 2, and finally at the end we have level 3. So we can compute the level graph in O of m plus n time. You just run a BFS and then you either delete the back and side edges, or you simply just create a new copy of the graph where you only add these edges. So here we only have so in the level graph, if we have a shortest path, ST path in the level graph, then it's also a shortest path in G, the original graph. So we can work with the level graph instead of the original graph to find the shortest path. So here we have a level graph L, and we have f and f prime as the flow which is before and after the augmentation. So we have L and L prime, which are the level graphs of GF and GF prime. So this is the level graph before the augmentation. And here we have found a path. And this is after the augmentation. So we add back edges to the graph after the augmentation. And then if you have any path with a back edge, it's going to be longer than the path you had before adding this. So you're going to increase the length of the shortest path here. However, there are cases like here where we still have another path, shortest path, which is of the same length, so we could take that next. But if you do this enough times, you do these augmentations at most m times, then the length will strictly increase. So what happens is the edge with the bottleneck is going to be deleted from the level graph after each augmentation. And then there's no new edge which is added to L until the length strictly increases. So the algorithm we implemented earlier, we didn't strictly look at the level graph, but this runs in O of m squared times n time using this BFS method. This can be improved upon. You can decrease the time spent per augmentation. So you have a data structure made by Sliter and Tarjan, which is called a link cut tree. It's quite complicated, but this allows you to reduce the time complexity into m times n log n. Yeah, so yeah. Okay, so the blocking flow algorithm. We have two types of augmentations here. We have the normal one, where the length of the shortest path does not change. And then we have a special case where the length increases. And so here we will explicitly maintain the level graph. And we start at S, and then we just advance along some edge in the level graph until we reach T, or until we just can't go any further. And if we reach the sink T, then we just update the level graph after augmenting the path that we have. If we get stuck, we delete the node from the level graph and go to the previous node. So we don't need this node anymore. So here we've advanced to T. We augment, and then the path has, or the bottleneck capacity is gone. So again, we advance, and here we can't reach anything. So we delete the node we're at. Wait. The color of S is not supposed to change, it's still in our path. We delete the node here, and then advance again. So we go through this path and reach T. And then we augment and update, and then advance, and retreat. So we delete the node, and we're done. We can't do any more. So here is the algorithm in the different steps. We have the initialization, we have the advancing, and the retreat. So these phases can be implemented to run in O of m times n time. First we initialize, which takes O of m time using BFS. We have then at most m augmentations per phase. So that's O of m times n per phase. And then we have at most n retreats per phase. We can most delete every single node in the graph. And at most m times n advances per phase. So this algorithm runs in O of m times n squared time. So you see, it's a bit better than what we had before, because now because the number of edges is usually going to be larger than the number of nodes. So here you can see some comparison between the algorithms or the methods used. So we have the standard augmenting path, which has n times c augmentations at most. So the running time here is O of m times n times c. We had the fattest augmenting path, which selects the absolute maximum bottleneck capacity. We didn't look at this in detail, but then we have the capacity scaling algorithm, the one we did look at, where we reduced the delta parameter by a factor of 2 at each step. There is an improved version of this, which changes an m here into an n, so it's a bit better. The shortest augmenting path gives us an even better time complexity, and it's really it's simple to implement. So for here for example, you'd need some sort of priority queue or something, to a data structure to maintain everything. Like, what's the maximum path? The blocking flow algorithm improves on this a bit, and then using dynamic trees, the link cut tree data structure, you can get something even better. Then we have algorithms. So the first method was just to use a simplex to just it's like linear programming to try all the values. we have some algorithm which uses a method known as a length function, which has a pretty good time complexity, and then quite recently something called a compact network by Orlin. This is a very good time complexity. It's number of edges squared divided by the log of the number of edges. And we're still searching for just a linear algorithm for max flow. Yeah, then there's something called push preflow, push relabel algorithm by Tarjan and Goldberg. And this increases the flow one edge at a time instead of an entire augmenting path. And maybe a fair warning to give out. When you're using the time complexity of these algorithms, they generally run much faster than the worst case. It's extremely difficult for some of these algorithms to create a graph which is the worst case. So even if the input seems large, max flow may still work. So even if it seems like it would take 10 to the power of 12 operations or something like that, or even more, then it could still run in less than a second. Because it's just so hard to create graphs which create these worst running times. Oh yeah, and this is the one that's best in practice. It's the push relabel method with some modification. Yeah, there are other cases where some other algorithms are better, such as computer vision. MaxFlow has a lot of applications. One more thing we want to look at. This is for bipartite graphs. So, which MaxFlow algorithm should we use if we want to find a bipartite matching? If we use the generic augmenting path, then it's going to be O of m times n. If we use the capacity scaling algorithm, it's going to be m squared, and blocking flow is m times n squared. So does this mean that the sophisticated algorithms are worse when the capacity is so low? And in fact, it just needs some more clever analysis. So if we use the shortest augmenting path algorithm, we get something which is m times the square root of n. And I want to look at a bipartite matching with you in code. So So let's say we have a problem where we're given the size of one set and the size of the other set. Maybe this could be, I don't know, people dating or something. And you want to match as many, you want to have as many couples as possible. Yeah, and this is what was a common example used in the past. So you had, you had n men, you had m women, and they have, like, these two people are willing to date each other, and then you want to find the maximum one. So we'll get the. It's often good to visualize these bipartite graphs as a left and a right. So I'll say we'll get the left and the right set, and then we'll have the number of edges. And then we'll read in L R M, and so what we do is we set up the let me open the graph editor. So we set up the bipartite graph. So you have the left part, something like this, and we have the right part. And then we add a source here and a sink here. Okay, and then we add edges from the source to everything on the left, and from everything on the right to the sink. Okay, so each person here can choose one. So the capacity on each edge is gonna be 1. So we'll have capacity 1, capacity 1, capacity 1, and capacity 1. And similarly on the other side, you'll have capacity 1 here, capacity 1, and capacity 1. And then you just add the edges which are given between here, between the sets, and they also have capacity 1. And then the max flow will give you the assignment of the bipartite maxing. So if you add the edges like so, something like this. So then, for example, the max flow would give us this matching. So we'll have this edge, we'll have this edge, and this edge. And you can see we'll have flow from here to here, which is 1, flow from here to here, which is 1, and then from here to here, which is also 1. So the size of the maximum bipartite matching here will be 3. Okay, so let's get the flow network we had earlier. Copy that. Okay, so we will have the source node and the sink node, and then the rest. So I'll say source equals 0, sink equals 1, left equals 2. That's where the left set starts. The right set starts at left plus the size, or the number of nodes in the left set. And the total number of nodes is then gonna be right plus the number of nodes in the right set. So we'll have a flow network which has count many nodes, and then we'll go through all the edges we're given. We get A and B. And this is an edge we have to add. And then we'll have to add all the edges from the source and all the edges to the sink. So let's add to our, oops, I forgot to define the variable name here, G. So let's add here to our graph from left plus A to right plus B. So this is the number of the node in the left set and the number of the node in the right set. The capacity should be 1 here. And then we have to add the source edges, so that's to all the nodes in the left set. We go from the source to left plus I and capacity 1. And then we do the same thing for the sink. We add an edge from right plus I to the sink with capacity 1. And after doing that, we want to output the max flow from the source to the sink. Okay, so let's try inputting the graph we have here. So let's number the nodes, so this is clear. So this is S and this is T. This is gonna be 1, 2, sorry, it has to be 0 indexed. So this is 0. This is 1. This is 2, 3, 0, 1, and 2. Okay. So our graph is we have 4 nodes on the left, we have 3 on the right, and we have 1, 2, 3, 4, 5 edges. Okay. We have an edge going from 0 to 2. We have an edge going from 1 to 1, from 2 to 0, 3 to 1, and 3 to 2. And we get the maximum bipartite matching is of size 3 here. Okay, but let's add some more. Let's try to get the matching. So we'll go through all the nodes on the left. And we'll look at all the edges there. So that's gonna be I is less than G, the adjacency list, of U of left plus U, size of that. So we're going through all the edges. And we only want to look at forward edges. So if G, sorry, left plus U, the ith edge is forward, then let's output U, let's output the so this edge, let's output the vertex it's going to, but we need to offset it by the value of right, so subtract right, and let's output the capacity of the reverse edge for this one. So it's going to be left plus U I rev cap. And let's run the same sample again. That's right. Okay. So here we have 0 to 2 with value 1, 1 to 1 with value 1, and 2 to 0 with value 1. So that means that our max flow algorithm selected the bipartite matching 0 to 2, 1 to 1, 2 to 0. The others are not in the set because they have a value of 0. So we're using the capacity of the reverse edge to determine what our selection was. Okay, so let's see if we can solve some problem with this. So in the high school competition here in Iceland, a couple of years back we had a problem known as t-shirts. Here it is. So here we have a bunch of contestants and a bunch of t-shirts, and the contestants are happy with t-shirts in a specific range of size. And we want to assign a t-shirt to every single contestant. What we want to know here is just a Boolean answer, yep or nip. Yep meaning that there is a perfect matching. So every single contestant can get a t-shirt that he is happy with. Okay, so let's solve this. Again, we're gonna need the flow network, so I'm gonna get that again. Okay, so the input we get
I'm sorry, is this also a version of stable matching?
yeah, so one of the applications of MaxFlow is for a stable matching. But I'm trying to recall if it was for us, if it was some modified version, not the same as the Gale-Shapley algorithm, which is commonly taught. Oh, I'm running out of time. Okay, let's see. I'm gonna change the problem a little bit. I'm gonna change the sizes to certain sizes. So let's have a small to extra large. Or extra small to extra large, rather. So we'll have extra small, small, medium, large, extra large, and one more, extra, extra large. Okay, so we'll need a map for these. So we'll have extra small, that's the smallest one, it's gonna be 0. We'll have small, which is equal to 1. We'll have medium, equal to 2. We'll have large, equal to 3. Extra large, equal to 4. and extra large equal to 5. Be a capital L. We'll have some number of test cases. I was confused. It wasn't this problem. It was there was another problem, which is also on UVA. Sorry. So here's the statement. I'm sure I had this as a problem. Yeah. So let me download the PDF and open that instead. Here. It's a short statement. We can go through it. So our friend Victor participates as an instructor in an environmental volunteer program. His boss asked Victor to distribute N t-shirts to M volunteers, 1 t-shirt each volunteer, where N is a multiple of 6 and N is greater than or equal to M. There are the same number of t-shirts of each one of the 6 available sizes, so extra large, large, medium, small, and extra small. Victor has a little problem because only 2 sizes of the t-shirts suit each volunteer. You must write a program to decide if Victor can distribute t-shirts in such a way that all volunteers get a t-shirt that suits them. So here we have some sort of assignment we want. So the input is given. There are a number of test cases. Yeah, so number of test cases, and then N and M. And then each volunteer is okay with some 2 sizes. So we get N and M. Again, we want to define the indices of our nodes. So we'll have source equals 0. We'll have sink equals 1. Left equals 2. Right equals left plus... so our left set is gonna be the t-shirts. So we'll have size of num, which is gonna be 6. And then the total count is gonna be it's gonna be right plus M. Because it said that N is the number of t-shirts. It's a multiple of 6 because there's the same number of each t-shirt. And then the number M is the number of volunteers. So the right set we have is the set of volunteers. Then we create a flow network. And we want to read all of the preferences that we have. So for each person, we have m of those. We want to read the two sizes they are happy with. So A and B. And we want to add an edge between those because they are compatible. So let's add an edge from left plus num of A, so that's the t-shirt, to right plus I with capacity 1. Okay. And then let's do the same thing for B. Okay, so now what about the source and the sink edges? So let's think about this. So each contestant, no, not contestant, sorry, each volunteer gets one t-shirt. But how many t-shirts do we have? Well, we have n divided by 6 of each. So the supply that we have here from the sink should be n divided by 6 for each t-shirt. So we'll have I is less than the size of num and then we add an edge from the source to the t-shirt, and we have n divided by 6 capacity there. And then similarly, for sink, for each person, we add an edge from the person, so right plus I, to the sink with capacity 1. Okay, and then we're only supposed to output yes and no, but we can get some more info, such as the matching that we have made. So first of all, let's output the maximum size, so max flow source to sink, and then let's again go through the left set and see who gets what. Size of num, check if it's a forward edge. So if it's forward and the capacity is 0, so t-shirt number I will go to volunteer number the endpoint of this edge, so that's left plus I, j, v, minus right. Okay, so let's get the sample. Okay, so for the first sample, we got the maximum size is 6. We sent an extra small t-shirt to volunteer 3. So volunteer 3 is 0, 1, 2, 3. Here, you got an extra small. Volunteer 4 got a small one, so that's here. Volunteer 5 got a medium one, so here. Volunteer 0 got a large one. Then extra large for volunteer 1 and extra large for volunteer 2. Okay. So in the problem we wanted to answer yes or no whether we were able to distribute them in a perfect way, so everyone gets a t-shirt. So now we just need to check is the maximum flow equal to the number of volunteers? If it is, output yes. If it's not, output no. And then we can comment this out. Yes, no, yes. Which is what we wanted. Yeah, that's it for the lecture. I will post the slides as well as some other slides which expand on this if you're interested.
Is it?
What?
I'm just asking if this is the last problem set, yes?
Yeah. So tomorrow we will do a review for the exam. If you have something you want to review, either just a topic or a past problem, then let me know before. So let me know today so I can have it ready tomorrow.
Okay. Yes. The question is, will we get some code from these slides?
The code from these slides?
Oh yeah, like I'm just thinking about the all these algorithms.
You will get the slides, but you will only get the flow network which I implemented now.
Okay.
It should be sufficient, I think.
Okay.
But you may need to modify some things for some problem.
Yeah, because all this stuff is pretty.
Yeah, it's hard to get into.
Yeah.
Yeah, so the problems, let's see. The problems we have now are max flow, paintball, min cut, elementary math, and min cost max flow. Here you have weights associated on the edges, and you want the maximum flow with a minimum cost. Then we have two bonus problems, science and eco cover. Each of these problems here are worth 1 point, and you need 3 for full marks. Yeah. These are just pretty raw. Maximum end cut. No story. Just do what the statement says. Yeah, any questions at the end? Gonna start by putting the slides online. Okay, then good luck, and remember to let me know if there's something you want to review tomorrow.